discrepancy between a miniature desktop thickener and a practical thickener come from? Okay. And really, what it comes down to is ineffective. So, we go back. It comes down to ineffective utilization of a thickener's volume because of adverse flow effects through the thickener. So this is how we structured our research process. We did a lot of scale model testing. We were then moved on to CFD simulations, computational fluid dynamics. And finally, we started looking at pilot plant trials. For the scale model thickeners, we used two types of thickeners. A 1 meter diameter scale model, shown here, and then a 400 millimeter scale model, shown here. In both pictures, you can see a mirror tilted to 45 degrees underneath the 1 meter scale model, and on top of the 400 millimeter scale model. Now that means when you are filming from in front of the 1 meter scale model, or from this angle for the 400 millimeter model, you can have a simultaneous front and top view. For the CFD, we used Flow EFD, which is a very nice user-friendly package and was giving very good results. Okay. What we're showing here is the 400 millimeter scale model with a low mud bed and operating with a rise rate of approximately 3 meters an hour, 3 to 4 meters an hour, which is fairly typical for most thickeners. Now this is with the open feedwell. I'm sorry, I haven't explained something. Let me backtrack a bit. What we are doing here is we are not running a thickener with actual feed, but instead we are pumping exchange resin through the thickener, which has very similar characteristics to a flock. It's got a very similar density of approximately a specific gravity of 1.02, and so we call this a flock emulator. So let's have a look at the footage. At a low speed of, this is a medium speed of about 6 meters an hour rise rate, and a very high speed of about 9 meters an hour rise rate. And you can see that everything starts to cloud up in the thickener body. Now this is not desirable. What this means is that lots of these solids will actually be washed into the launder, and you won't get clear overflow. In fact, you'll be drawing some solids into the overflow, which of course is not desirable. If we have a look at the comparisons with the CFD simulation, we can see much the same here. It enters tangentially, and then it spins around the feedwell and exits mostly opposite to the feedwell, the feed pipe. We are seeing a couple of adverse flow effects here. One is a very high velocity tail down there. The second is what we call a radial recirculation, where it is moving